What is up, everybody? Um, I apologize for the long wait. I had some personal stuff going on, and then we got snowed in. Actually, we had snow for once, so that was pretty nice, and I was just enjoying that. A little bit of an extra break that we had. After the last video we made, and we were working on the last challenge, I had to take a break from it just because I wasn't really getting anywhere or getting any new info. So I mean, I was intending to take like a day break or so, but then I was like, you know what? Like, I have some days off. I'm gonna play some games, something that I don't do very often, and so just enjoy my time off. But this should be the last day that we're snowed in, and so with that said, I'm gonna go ahead and get back into it. Now while I get this loaded up and double check my stream, I did end up solving the last challenge. It was I solved it in a very unexpected way, and so I don't think it was ideal. Like, it was the only way I could see that we could solve it, and I'm starting to think that it was the only way to solve it. But it was very weird how we did, or how I ended up solving it. So I'm gonna go over that and try to see if I can see any more patterns, because, well, you'll see. Okay, that's working. I don't know why it's going to the speaker still, but it's all good. Alright, so if we go over here, so this is a script that I made to solve it. To put it shortly, for some reason, the last 4 bytes after the Canary affect the return address, even though it doesn't directly overwrite the return address. I'm not entirely sure why. That's why I'm gonna take this bit of the stream and explore it a bit more. But yeah, so essentially you set the 4 bytes to whatever. Really, I don't think it makes a difference. I tried various inputs to see if it gave me any different outcomes, but it's truly it's random each time. However, I saw that with this, a lot of the times the return address landed somewhere inside the buffer, and so, you know, if it lands anywhere inside the buffer, that's pretty much complete control, because it gives you have the string inside the buffer, and then in that last video we saw that it loaded the effective address of whatever it was pointing to, and so it'll dereference that and give us the function we want to return to. So let me go through and show you. I'm going to show you the working exploit. So it doesn't work every time, like I said, but most of the time it does. Let's just wait for it to prompt all the way. Oh my gosh. There we go. So yeah, it's very weird, and honestly it's frustrating, because I thought we were supposed to like overwrite something in the global offset table or the procedure linkage table, but in reality it was actually much simpler, kinda just a little weird. So if we do, okay, if we go back and change in our script to do it locally, and we run it, get the process ID and attach with pwn debug. So if we get out of these, and you'll see here, it says print banner for some reason. I'm not entirely sure why. Because if we look here, (804.926C), that's the read flag function. It's not print banner. I'm not sure why it's saying that in pwn debug, but yeah, you know, whatever. We know it's the right address. So if we step to the next call, it'll, yeah, let's just show exactly what happens first. And we'll put thanks for using tweet to the stack, move that, compare the stack Canary, move, okay, so it's in relation to the base pointer, right? So whatever gets put on the stack and then in relation to the base pointer. So at times, let's see, if we examine that, so ff9caf00, there's 4. ff9caf14, let's examine the stack pointer now. Oh, oops. So caf ff9ca ef. Okay, so it's much lower. Okay, so I think F10. It's 14 right here. And then if we examine, let's go through each of these and examine what's at them. Right, so it points to whatever's on the buffer. I'm not sure if this is the address of the buffer. And the reason why I say I'm not sure is because, for example, okay, so ff9caf, buffer is the overflow is like 200 something bytes, so these last two numbers are the only ones that matter. So you have this, you have this, you have this, and then you have this. So we saw that there was 4 addresses, and for some reason it's using those as the return addresses. I'm not I honestly don't know why. Well, anywho. So, bear is pointing to somewhere in the buffer. Leave, and then ECX -4, which would give us one index, or no, 4 indexes lower, and that still points to read flag. So Yeah, and then this will repeat 4 times for some reason, even though they're at completely different locations in memory. Not sure why. Well, I guess because. Oh, well, yeah, that makes sense. Whenever you load it into, or whenever you make the stack pointer point to that buffer, that portion in the buffer, it's whatever's left on it. And so because we're pointing it at an index where there's 3 more after, then those are going to be the return addresses for the next 3 iterations, or whatever you want to call it. But yeah, really, really interesting stuff, because it's not how I was expecting to solve it. And we can change this too, but like it's not gonna change anything really. I tried to see if there was a pattern to it, but it's literally just what is on the stack at the time in relation to the base pointer. So if you happen to have an address that's pointing to the buffer at EBP minus hex4, then you will get your read flag function executed, but otherwise it'll do something else completely random based on whatever the address is there. Now, I don't know, this is also very strange to me, because if you I'm gonna have to go through this again and take a little look. Interesting. Well, not interesting now, because it doesn't really matter. If we exit out of the program, let's put that up again. 2215. See, now it's pointing to somewhere towards the beginning of the buffer, because if we do backtrace, that's pretty much our entire buffer right there.
We played together on that island. His voice always used to be there. Now it's gone. I can't think of his face or his name. I feel awful.
120. That's the Canary, I believe. Where's the Canary at? Okay, it's right there, I think. Yeah, that's the Canary. That's weird. I guess because it's 4 bytes of overflow, maybe it's pushing it in some way. No, that can't be it. Because we're writing to memory, it's not like we're doing like anything like that. 482. 200. That's right here. To zoom the base pointer. Okay, that's interesting. Okay. So, okay, I think maybe I know what it is. Maybe. But it's confusing because I don't know how that would work exactly. Okay, maybe let's try observing it without the 4 bytes overwritten, because that'll give us every time it'll give us the libc start main as a return address, but it's pretty clear that we're not overwriting it, because otherwise it would point to whatever I have here. It would point to whatever I have there, so it's not overwriting it. So maybe I am right. Maybe it is somehow pushing it. Well, you already know what this is going to do. We're not getting any new info here just by following the execution of the program. We have to look at how it relates to the base pointer. So let's comment this out. Let's do this. So FFED 9070. 9070, that's right here. Text 1, it doesn't point to anything. What about our stack pointer? Canary, this is the null byte after the fact, FFED 9070. That's where the base pointer's at. I wonder if we can get any more if we just do this. Okay, let's P minus XC. Maybe P minus XC. Minus X4. Let's put FFED, that's pointing to that. And then ECX minus X4. 6C, 6C, I think. Just pointing to that. Yeah, okay. So then it'd be helpful if we could inject the payload and start at main. But unfortunately, if you do that, it goes on an infinite loop, which I don't understand. But yeah, 6C. Interesting. And then it returns like normal. Let's try making it a little more helpful, maybe using that instead. And of course, our language server gets all messed up for some reason. Statements, semicolons. Dude, what are you talking about? Semicolons. Oh, that's fine. Duh. 1, 2, 3. Exit. See, in times like this, it won't always point to that. So we have that right there, the Canary, that, and 804, 8034. Interesting. base pointer. I forget. Leave instruction assembly. 32-bit. Set ESP to EVP, stack pointer, base pointer, pop, whatever's at the stack pointer into EVP. Okay, cool. Then it loads whatever's at ECX minus hex 4. So let's do when I just pull up the calculator. The address. 4. It's FFB6 35 FC. Okay, no, I was right. FC 34803 which is TSP. That's that instruction there on the stack. Huh. Stack pointer now. Somewhere in the stack. Read flag. Then we get, for getting a hex for this, that's where the base pointer is pointing at, BF04, 804, BF04. Which I don't think points to anything. Oh, it does. Okay. So none of these calls have an effect on it. Same thing there. Same thing there. And whatever is at EBP minus hex 4 gets dereferenced, which will be read flag. Leave will set the stack pointer to the base pointer, and then pop it into EBP. Set stack pointer to whatever is pointed at by EBP. Set the stack pointer to EBP. Shoot that. And pop into EBP. Huh. So the base pointer is pointing to actual return address. So that's how it is with function on the exit of a function, at the end of a function. But because this isn't using your typical function epilogue, it is doing something different than whatever we get at the stack pointer right here. I'm sorry, whatever gets set right here, whatever address is right after the stack, after the 4 bytes, return. Okay. Okay, so my best guess would be that whenever these 4 bytes aren't there, this is usually libc start main, so it's got to be pushing it in such a way that Um, let's see here. Hold on. Yeah, it must be pushing it in such a way that where it's where typically this address after those 4 bytes would be the offset to libc start main, but then when we overwrite the next 4 bytes, it pushes it in a way well, hold on. Let's do one more time. This will be the last time I'm doing it. Because to be quite honest, it's I'd have to do some research. So I don't think I can come to a conclusion just based off of this stuff. Or like what I'm seeing. It's probably has something to do with the internal workings. So F7 CCB 29E. Examine the address at the base pointer. Major 4 BF04. Fix 4 BC. That's irrelevant. Let's look at 4. this is completely different, actually, than what it says right here. Because if it was following these instructions... Oh, interesting. Flags are set. Parity interrupt. No flags are set. These are all exceptions that are raised. So it's doing it completely different than what it says here. So this should be libc start main though. Okay. So I guess due to there not being a function epilogue, that the leave instruction is different. But I'm not sure why. Let's do some instruction. So literally because of the lack of a function prologue or epilogue, because this was programmed with omit frame pointer, that the leave instruction is irrelevant, but it also doesn't do what it's supposed to do. But because you're loading whatever's at the base pointer, then based on whatever's on the stack, ECX minus hex 4 can give you the address to the buffer, somewhere in the buffer, since they're both fairly close together, I guess. That's my best explanation, really. So anywho, it's pretty fun. This is just explaining what the options do. Okay, they don't need one. Displays the instruction to save, set up, and restore the frame pointer. Some targets this flames in fact. Yeah, doesn't guarantee the frame using all functions. Okay. buffer. See if this gets us any explanations. Yeah, I'm not really finding anything. So I guess the conclusion is that because the base pointer address is most of the time relatively close to that of the buffer, that is why we can exploit it, because there's no pattern. It's literally just whatever happens to be. Well, okay, I say not a pattern, but if we don't add those 4 bytes, it's still pointing to libc start main, so we're not overwriting it, but I think we're pushing it in such a way that it influences the return address. I don't know. Because that's the thing, no matter what input we give at those 4 bytes, it still does the same thing. Which is why the push thing would be the best explanation. Thing is, maybe we could attach in our script, like do gdb.attach, but the problem with that is that for some reason it doesn't work. I don't know why. So Hmm. I don't know. Either way, I can't waste too much time on it, unfortunately. I got other stuff I gotta do. So I will be right back. I gotta use the bathroom, and then we will start the next challenge. Alright, I'm back. Okay, so yeah, I've decided that we will go over this in a later video whenever I'm done with like all the challenges that I'm doing write-ups, and we'll investigate further. I also, just real quick, I wanted to look here and see what functions are available in regards to GDB. Attach an existing proxy, IDs, debugger, stuff for instruction. Like if you're random matter for debugging. Let me check something. Okay, GDB works. Let's see if it. Command context will execute properly. Yeah, see, for some reason, whenever I installed Pwn debug, it did that. So, Python image documented. Script. Let's just select the program state. GDB script. See, I'm trying to figure out right now why attaching with GDB isn't working. I don't think that's relevant. We can try. Yeah, I mean, let's there. from here, I guess. Ah, there we go. I'm not sure if it, I'm not sure if that worked, but... Buffer over. Okay. Okay. So I guess we just had to start it in an actual terminal instance. But it didn't actually break anything. Okay. See if I could just change it to use pwn debug. Wouldn't be an issue there. Okay. So literally
didn't know if you were busy tonight, but
does nothing. Okay.
just if you're around, give me a
Well,
text.
whatever. That's something I gotta work on another time. Anywho, yeah, let's move on to the next challenge. Hello. Oh, it shows open file, not open folder. Okay, so the next challenge to get this started up. This one is full protections, and it's going to be interesting because since it has full protections, if we go here,
Second thought, never mind. These came up.
let's see here. sorry, but like I was saying, because it has full protections. Well, let's see what protections exactly it has. Let's undo. Should be somewhere in here. We might have omitted the compile stuff. Oh, never mind. Right here. Optimizations. It does have debug symbols. Stack protector, compiled with PIE. Oh my gosh, that's a lot. Our main concern here is PIE, because that means it randomizes where the binary is each time, which also means that we gotta predict or find the offset. Well, we would have to leak where it's at. And luckily I took a look at this the other day and saw that when we start the program, that's the main address, so we leaked the main address already. So then all we have to do really is find the offset into libc, and we can do like a ret to libc depending on what primitive we have. Should be a function. Like the other functions that we saw. Oh, here. Read memory, write memory. So it's got Canary protections, no stack, no execute on the stack, and PIE, and full relative read only, which means we can't overwrite the global offset table or anything. So that's interesting. It's going to be very interesting. My main thing will be the Canary. Let's see. This is a character buffer. redundant lines, but whatever. There's 4 and value pointed to by unsigned integer 8-byte pointer to var 35 plus ex4 equals a new line. Okay, so that's just checking if the last thing we put was a new line. Not too bad there. It's going to replace it with the null byte. Let's see, buffer. Why is that casting it to an unsigned integer? Hex 31. Okay, so this is just going through. Can I? Oh, and value pointed to by character pointer buffer plus 1. Value pointed to by the pointer character pointer cast plus 1, so the second index. And that doesn't make any sense at all, actually. Address of the buffer plus 1. So go plus 1 byte, so that's the second index. And then since it's casted to an integer pointer, the value pointed to by it. What is that doing exactly? That doesn't make any sense. I guess it's checking to make sure there's no character after, so if a character does exist, that would go to false, and it would go somewhere. What a weird branch here. It's not equal to 2, or another value exists. And if equals to 3 and there's another value, put by. Put no. And then we have 2 continue statements. Better break. We also don't need 2 breaks. Wait. Why is Those are 2 breaks, dude. Oh. I think I messed up. Oops. Also, I'm not super familiar with Binary Ninja, so I'm kind of feeling my way through, just getting a feel for it. 31 equal 32, not equal 33. Okay, that makes more sense. Buffer not equal to 33. Nah. Not equal to 32. So if it's an invalid number and it's testing at 2 for some reason. Oh, so I guess it's checking numbers by testing what it's not equal to and then puts by, breaks from that. If it's not equal to 31 or just 1. Then this is the branch that executes. That doesn't make sense either. I think it should be equals. Yeah, so if buffer is equal to 31 and it's not a character, then it'll read memory. Otherwise, if buffer try inverting it, no. Maybe you should just restart this Discord. So I guess it's hard-coded. this? I guess, I just do indexing. Oh my goodness. Okay. Let's discard and restart. This is literally it's a buffer. I mean, I don't know why it read it as just a character. And then that's from standard input, so read 10 bytes from standard input into this buffer. Let me just double check. Oh my, get out of the way, man. So I guess we can try no. Buffer. Okay, there we go. So if buff 0 equals x31 and buff 1 doesn't exist, that is a lot better. There we go. Okay. And then I mean, the branching doesn't really make too much sense, but we can see the flow, like, kinda. If EDI, where's EDI at? EDI equals 0. What is this keeping track of? EDI plus equals 1. EDI equals hex 64. So I guess this is keeping track of how many prompts we give it. I wish you could rename variables. Why is it not? Maybe type. So prompts given. Can we rename this to put buffer? Prompts given equals hex 64. What is hex 64? So 100 prompts is the max. I guess that's to limit like brute forcing. EX4. Also change this to length input. String length sent back of size T. T. No? Okay. Why not? Okay, I don't know why it's not changing the type. It should be main, right? It should be character buffer. Should change this whole expression. Can we? Hmm. Not gonna do anything. Okay. No. No. It's gonna be I know what it's supposed to be, I just don't know why it won't let me change it. It's literally just the character buffer plus that. If I change this, no, it's not gonna let me change it. Why? Oh my gosh. define it. Variables to merge with. Okay, no, nothing still. Name should be. No. Gosh, this is so annoying. Both of these are declared and initial. Technically, I don't know why it's not letting me do it. No. Should we just do? Make it an integer. So this is supposed to be U size T. That's what that returns. U size T. Oh. Okay, that's wrong. Let's just undo that. But it's main hours equals host 10. That must be. Yeah. Why is it? That makes no sense. What is this even? Okay, now. Still the same stuff, okay. Even though this is the first declaration internationalization, so like what? Just not want to do it. That's very clearly what it's doing. It's indexing right here, the input buffer, so why is it not letting me change it? No. Oh wait, maybe. Value is input buffer. To initialize, can't be that either. Has to be a buffer. Okay, well, I guess that's as good as it's gonna get. We'll just try to comment. Close to the fur. And yeah, okay. Character pointer. It's from stream into the array pointed to by S until n-1 bytes are read or a new line is read. Oh. Return character pointer. Oh, I see. So it is supposed to be character pointer. Okay. X10. Delete the comment. Still won't change that type for some reason. Because it's still... understand why that changes it. Like, it's very clearly. Like, come on. Brother. Okay, I think I'm getting way too caught up in trying to fix this part because it's so stupid. It's literally, it's supposed to be the last index. Like, I don't get why it's making it so difficult. But whatever. Okay, anywho. that, guys. I had to check some messages. Alright, alright. That is gonna be bothering me a lot. Let's go to the other function, shall we? So first, I guess we should, so the stat Canary is going to be a little hard to get because, we're not using a buffer besides for bed line. We are using a buffer there, but there's not going to be an overflow primitive. But we know it should be right after the buffer. So if we can get the address to the buffer, we're good. Well, we'll see. Hold on. Let's just mess with it a little bit. Interesting. If prompts good equals x64. That's funny. I guess that's the address. First thing it prints though is the main function. So we have the address of the main function. Um, hmm. Didn't give us a node address. Okay, so I pointed out the address. This is all pretty simple to understand here. What units 32 value scan. Okay, so we're writing integers. Okay. Okay, so that's what we're working with pretty much. There's not a yeah, there's not like a read flag function or anything like that in this challenge either, so okay. Get the offset into libc right here. It's the offset that'll be important later. Main is that's the offset of main. See if it gives us that address. What's it calling print with? Interesting. Security. Oh, okay. Yeah, so it did print the main function, so we got that's for sure what that is and the offset of it. Okay. All right, so I kind of got an idea of what I want to do. So we have the main address leaked. Find the offset into libc that can give us, at the minimum, whenever we do exploit, we'll know where libc is at, the offset of that. I guess now it just because the stack will be in a different place every time, so we can't do that. Now I don't know if okay, so it should be asking us to write choice, and it should be prompting us, reading, yeah. Up to 10 bytes of input, and then okay, so that's invalid. Has to be a number, so we can't leak anything off the buffer since it's uninitialized. Paired byte pointer, base pointer plus EX times 1 minus 2D, so ABP minus 2D. Nah, it's fine. Interesting. Put no again. It's probably. Okay, this is pointing to the same portion of memory.
You know, love is an incredible thing, and we don't know love like we should.
Interesting. Because this is going to the choices. So it already printed the address. Let's try that again. Sorry about that, guys. I'm back. That'll be it for today, though. Today mainly was just to get an overview on what the program does, and of course I obsessed over getting the control flow and the decompilation correct, but I got an idea of what to do, so should be fairly simple approach. We just gotta find where exactly the exploit will be, which I think can be anything really, since it's writing to various locations in memory, which is interesting. Scan F, writing. Yeah, so. But yeah, we'll get back at it tomorrow, hopefully.